Way back in 1988, the November issue of Modern Electronics magazine featured an article by Lee Hart, who has been featured in some of my other videos as the creator, inventor, designer, what have you, of some other vintage computer equipment, like a 6502 name badge and the 1802 membership card, which is a Cosmac Elf reproduction, and some others. This is a non-microprocessor article, and is just a cute project for the home experimenter to build an electronic greeting card. It's sort of an odd title, but it's not a greeting card so much as it is a Christmas tree with LEDs for lights and resistors and capacitors as ornaments, using only a simple logic IC and no microprocessor or other controller. Lee Hart offers this as a kit these days for I think $9 through his website, which I'll show the link for. And I thought it'd be worth building, not because I want a Christmas tree ornament necessarily, but because it's a very clever circuit, and I thought it'd be an interesting video to do. So let's get into it here. These are the components you get with the kit. A single-sided circuit board in the shape of a Christmas tree. Very simple circuit, big wide foils, large pads. 3 green, 3 yellow, and 3 red LEDs. 4 resistors, 4 electrolytic capacitors, 4 ceramic disc capacitors, positive and negative connectors for a 9-volt battery and screws to go with them, and a logic IC, 4093. The kit doesn't come with an IC socket, but I always like putting sockets for ICs on most of the things I build, so I just took one out of my parts bin and put it on there. And the resistors go on next. They're all the same value. And then the LEDs go on. The kit instructions don't describe which place to put the various colors in, so I just decided to follow the photo of the kit creator's own example. Seemed like as good a arrangement as any. And then the disc capacitors go on. And then the electrolytic capacitors go on. And then the 2 9-volt battery snaps are put on with some small screws. And then finally the IC snaps into the socket and kind of makes the trunk of the tree. Now the idea here is that the board doesn't weigh very much and the battery weighs quite a bit, so when it's snapped into the base, it actually makes a stand that holds the tree up. There is no power switch, so it's simply inserting the battery. So I want to talk a little bit about the way this circuit works and what makes it interesting. The 4093 IC that's on the board here, I don't know if my camera's quite going to focus, there we go. 4093. This is a CMOS logic IC, and here's a hand-drawn pinout. It contains 4 NAND gates, but they're not just regular CMOS NAND gates, they have Schmitt trigger action on them. A normal CMOS gate or a logic gate would transfer or react to an input signal at about half of the power supply voltage. This is a 9-volt battery powered circuit, so 4.5 volts is the halfway point. So when an input is greater than 4.5 volts, the input will react to it. If it's less than 4.5 volts, it will react to it as a logic 0. The Schmitt trigger, on the other hand, is a little bit different. It reacts differently with different voltages depending on whether the signal is going from low to high or high to low. On a rising signal, the voltage has to be more than halfway up between 0 volts and the power supply voltage before it recognizes the input. On a signal that's dropping from power supply voltage down to 0, then it has to go beyond the halfway point in the downwards direction before it recognizes that the input has changed. This allows hysteresis to be used in circuits, and Schmitt-Trigger logic devices are commonly used for debouncing or noise reduction on noisy digital signals. But here it's used a little differently. All of the AND gates, or NAND gates rather, in this circuit are configured the way I've drawn on this sketch, with both inputs tied together. Now with a NAND gate, if you tie both inputs together, it behaves as an inverter. So if the input is logically high, then the output is logically 0 or low, and if the input is the other way, low, then the output goes high. So it turns a high to a low and vice versa. But again, it doesn't do it at the halfway point. So when the signal on the input is going from a low value or a logic 0 to a high value or a logic 1, the voltage must exceed half of the supply voltage before the inverter function recognizes it and flips the output to a logic 0 or a low voltage. Then when the input voltage is dropping, or going from a logic high to a logic low, it has to go below the halfway point on the voltage of the power supply voltage before the output then flips back to a logic high. Now, a classic way to make an oscillator with logic ICs is to take an inverter or some other inverting element and tie a resistor from its input to its output so that the output is fed back to the input, and then to slow the circuit down to force it to make its changes gradually, a capacitor is placed between the input and ground. So let's say the input is at a logical high, the output will go to a logical low, and it'll try to drive the input to a low, which then would turn the output high, and it goes around and around and around, and it will oscillate, but it'll oscillate very quickly. By putting a capacitor here, it forces the capacitor to charge, and because of the resistance, it takes some time to charge it. The voltage here slowly changes, and then it has to reach the threshold of the input. So let's take the scenario where the output is now a logical high, and it's trying to charge this capacitor up through the resistor. As it does so, the voltage here slowly rises, and because this is a Schmitt-Trigger device, the voltage has to rise above the halfway point before the input recognizes it. At that point, it sees it as a logic 1. The output then flips to a logic 0 because it's an inverter, and now it tries to discharge the capacitor from its previously high voltage state back to a voltage of 0. Remember, the output's 0 now, but it doesn't do it instantly because now it has to discharge the capacitor through the resistor. It takes some time to do that, and this voltage slowly decreases, and when it decreases past the halfway point, then it recognizes it as a low logic signal that flips the output back to a high, and the process repeats. So what you actually have is an oscillation here. The input is acting in an analog fashion with the voltage slowly rising and lowering, and the output, because this is a logic device, is snapping between logic high and logic 0 in a digital fashion, and then the difference between the digital section at the output and the analog section at the input is due to this resistor-capacitor network. The formula for the frequency of oscillation in this circuit is 1 over 1.4 times R times C. The actual values in this circuit are 5.6 megohms for the resistor and 0.1 microfarads for the capacitor. So substituting the abbreviation there, that's 1 over 1.4 times 5.6 megs times 0.1 microfarads, which in my abbreviated scientific notation looks like this, and then calculating it out, you're 1 over 0.784, which comes to 1.27 hertz. So the circuit oscillates with the output changing back and forth a bit more than once a second, so pretty close to 1 hertz. Now a few words about CMOS if you're not already familiar with it. One of the advantages of CMOS logic is an extremely low current consumption, and especially valuable is that the logic gates take essentially no current unless they're actually changing states. So if you've got a steady state on the input and a steady state on the output, then it draws essentially no current. But if you do make a transition from low to high or high to low, it uses a very small amount of current only momentarily, and then goes back to a non-current using state. So CMOS logic circuits, especially those that are running slowly, use essentially no power. They can just run almost forever on tiny amounts of power. So looking at this circuit here, the capacitor doesn't use any power. The resistor does drop something, but it's a very high value of resistance. 5.6 megs is a lot, so the current through it is very low, and that's why we can use such a small value capacitor for timing purposes. Normally you'd use maybe an electrolytic capacitor with 10 microfarads, 100 microfarads or something, but with a smaller value resistor. By bumping the resistor up to such a high value, the capacitor can be very small, and the resistor being very high limits the amount of current even more, so this just reinforces the low power consumption. And this circuit can run for a long time, and it only uses just a few microamps of current, or has a few microamps of current going through it. It's a very small power usage. But having an oscillator doesn't do us any good on a Christmas tree ornament that has LEDs on it. So we need to eventually drive LEDs. Now here's a simple way of driving an LED off of this oscillator. The output of the logic gate just goes through the LED to ground. And of course the LED only lights up when current is going in that direction, so you need to have a high here, a logic high, so there's a reason for the current to flow in this direction. Now there's a downside to this, of course, that the gate will try to drive as much current as it can through this LED, and it'll use excessive current and burn itself up eventually, and it'll be very bright and won't last very long. So the way we usually handle this is to put a series resistor in there with the LED, and that limits the current through the LED. Some good rules of thumb for standard LEDs is say 1.7 volts a forward drop on the LED, and a good current for proper illumination of the LED is maybe 10 milliamps. Some newer LEDs work on a lot less, as far down as 1 milliamp with satisfactory brightness. But let's just say this is 10 milliamps with 1.7 volts. Now the circuit's running at 9 volts because it's powered off of a 9 volt battery. That means that the remaining voltage left over for 1.7 volts needs to be 9 volts minus 1.7 volts. So 7.3 volts. And we have to calculate the value of the resistor, which is easy to do with Ohm's law, because all we have to do is divide the voltage by the current to get the resistance. So 7.3 divided by 10 milliamps is 730 ohms. So far so good. But this LED will only turn on when the gate is at a logic high. When the gate is at logic 0, nothing will happen because it's at 0 volts here and 0 volts here at ground. No current will flow and nothing will happen. The LED will just be off. But the main thing we're worried about here is not just that the LED will only illuminate on the positive cycle, after all we do want it to flash, but that it's going to use up a considerable amount of power in the dissipation through this resistor. That resistor is not our friend when we want a low power circuit. Another way of limiting current is to use a capacitor instead of a resistor, but the downside of this is it only works if you've got an oscillating circuit, because a capacitor in series with a circuit will block DC. And of course this is a DC circuit. There is no alternation. There's oscillation but no alternation of polarity. Still, let's take the scenario of the LED being off and the output of the inverter turning on. When you first change current on a capacitor in series like this, it will act momentarily as a short circuit. So momentarily you'll seem to have current going through here and the LED will light up. But very quickly the capacitor charges so that both sides of it have the same charge, and therefore the current will stop flowing. And so you'll just get an LED that pulses briefly but then remains off. However, what happens when you change the oscillating element here, and now it goes from a logic high to a logic low, all of a sudden it's got a charge that's contrary to that, and it's going to discharge briefly, which will want to pull current the other way, but it can't because the LED only conducts in this direction. But what if another LED is put in parallel with the first LED and pointing the other direction? Now when the output of the inverter goes low, now we can charge the capacitor in the other direction by current going this way. And that will cause this LED to pulse briefly until the capacitor charges up. Then when the output goes high, it'll do the same thing in reverse. The capacitor will charge in the other direction. There will be a momentary flow of current, and this LED will momentarily flash on, then be off. And vice versa, as it oscillates, you'll first pulse this one, then it'll be off, then this one will pulse and it'll be off. This one will pulse, and back and forth. So now we have two LEDs flashing back and forth at a slow rate of a little bit more than 1 Hertz. And since capacitors don't really dissipate power in the way a resistor does, the only power being consumed here is what's consumed in the LEDs themselves. And it's not for that long, it's just for that very momentary pulse. So in effect what this little capacitor and two LED circuits is doing is it's acting as a kind of a power converter. It's converting a relatively high voltage, 9 volts, at a very low current into a lower voltage but at a higher current. This is the brief pulse of current that causes the LEDs to flash, and they flash quite brightly because that momentary pulse of current is relatively high. There is no resistor to lower it, so the current is just whatever you get from the discharge of that size of capacitor. The only real limiting element here to keep the current from being so high it'll destroy the LEDs is that the CMOS gate itself has some series resistance that will effectively limit the current to the LEDs to a safe level that will not destroy them. Well, this circuit has 9 LEDs, so how do we get 9 LEDs out of this circuit that I just described? Well, first off, let's ignore the one on the tip of the tree and just look at the other 8. that divides out, if you divide that by 2 for 2 LEDs per circuit, that means 4 circuits like that, or 4 oscillators, each with their own resistor and pair and capacitor and series electrolytic and 2 LEDs. However, here's another interesting thing about oscillators. If you're not controlling the voltage in such a way that each oscillator is isolated from the other oscillator's power supplies, they have a nasty tendency to slowly form into a lockstep arrangement where they're all oscillating exactly in sync with each other, even though the resistor values might be slightly different than the capacitor values, and they may start out oscillating to their own drum beat because they are approximately the same frequency, having the same period of oscillation, and they're on an unregulated supply, meaning this 9-volt battery. When they draw current, that causes a small change in the voltage applied to the other oscillators, and that causes them to sort of drift into lockstep with each other, and you end up with a very monotonous flashing display on the Christmas tree, where 2 LEDs or 4 LEDs always seem to be on together, then they go off, then 4 more LEDs always seem to come on, and it would be just like 2 banks of LEDs going back and forth, and it wouldn't have a nice twinkling effect that we're after. So the solution to this is change the arrangement of the oscillator and the LEDs to different permutations of the same basic circuit, so that they react differently to voltage changes, and therefore they won't form lockstep with each other. What if we flip the output circuit around but keep the oscillator itself the same way? So instead of the capacitor driving 2 parallel LEDs to ground, we now have 2 parallel LEDs to the positive power supply. Circuit's going to work the same way, except now it's sourcing current through this LED through the charging capacitor to a logic low here, and then when this goes high, you're charging the capacitor in the other way to put current in this direction back into the power supply. Same idea as going to ground, just the polarity's reversed. And what if we also flip the capacitor on the oscillator, so instead of charging and discharging relative to ground as it did before, now it charges and discharges relative to V+. This will still work. The LEDs will flash at the same rate, but the oscillator will be less affected by what's going on with the other oscillators. And we can also make the final change, which is to flip the LEDs down to ground instead of from V+ like this. So that's the 4th permutation. One good way to damage a solid-state circuit, especially one with ICs in it, is to apply reversed voltage polarity from the power supply, whatever it is, a power supply running off the wall mains or off of a battery or whatever. To connect it in reverse can easily damage the circuitry. So it's quite common to put a blocking diode in series with the battery or power supply like this, so that it can only conduct current into the circuit when it has the correct polarity. And this circuit is no exception. It should have a blocking diode too. But remember, it takes very little current to operate this circuit. So what if we didn't use a regular diode here, but used an LED instead? It's still a diode. It's still going to have blocking characteristics, but it's not going to handle a lot of power. If you put more than 20-30 milliamps through it, it's going to be damaged. But this circuit doesn't take that much current. It only operates on very small amounts of current, and therefore the LED can be used in this situation. And remember, we have 4 oscillators all going asynchronously to each other, and the oscillators themselves take almost no power, almost zero current, and the only time the LEDs consume current is during the transition of their associated oscillator, just for a very brief fraction of a second. So we do get a pulse of current that's, I don't know what it would be, I haven't calculated, but let's say it's 30-40 milliamps perhaps through the LED while the capacitor is charging, and the same thing through this LED when the capacitor is discharging. So you've got these pulses of current being drawn by this oscillator LED circuit, but the rest of the time it's almost nothing. You've got 4 of these going, but they're asynchronous to each other, so what you end up with is a bunch of pulses of current coming at seemingly random times, but with all 4 of them going, it's going to be several times a second, and that current pulse that's drawn from the circuit, drawn from the battery through the LED to the circuit, those current pulses are going to make this LED light up. And in between flashes of the LEDs, there's going to be almost no current, so the LED won't light up. So what we end up with is a rapidly twinkling LED, which is a good thing to do with that LED at the top of the tree, which is traditionally supposed to be interpreted as a star. And what do stars do? They twinkle. So this is a very simple way of getting a twinkling LED at the top of the tree, and that's exactly what this circuit does. So here's the battery plugged in, and you can see it makes an adequate stand. And here's the tree with its various LEDs flashing at different points. You may have noticed, for example, that these 2 green ones have kind of come into sync with each other, but they're going to drift off of that over time. I've watched it, and they do. And the twinkling LED on the top is a little hard to see on the camera, but it is twinkling. There you can see a little better. And there's a certain amount of persistence in the, I think the camera, I'm not sure why, on a digital camera, but on the viewfinder it looks like these 2 green LEDs are flashing exactly together, but in reality it's like pulse, 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 back and forth, and they're going to slowly drift apart. So these LEDs and their associated oscillators are not synchronized with each other, but because they're running at the same frequency, they can, for a while, appear to be in lockstep with each other, but it won't last. They'll eventually drift, and the pattern will constantly be changing slightly. So I hope you thought this was interesting.